bring you some of these really cool perspectives. And before we begin and get into the fun, I just want to provide my small sales pitch for why the Peer Student Committee is something you all should be engaged with, and also, I guess, like, consider joining and hopefully contributing to in the months to come. So I'm just going to go ahead and share my screen. We've created these stunning slides for you to enjoy here. But the idea is that really within the context of earthquake engineering, we are trying to bring together students, graduate, undergraduate, and also early career and mid-career professionals who are all interested in earthquake engineering and are specifically thinking about the connection between research, professional, and outreach initiatives. So what the PSC is just really a group of students across the peer institutions trying to bring experiences across these three different legs. And so we actually have people coming from a very wide variety of schools, and you'll see that in our leadership committee. And the idea is that this year, and hopefully moving forward, PSC is a very new initiative. We're going to be able to make this community even stronger. And so we're basically 14 officers from across the peer network with 3 targeted subcommittees. And this idea of one PSC, one community, hopefully us working together and being able to build this community. You can see our beautiful faces on the screen. Please feel free to reach out to us for any questions regarding the PSC. I mean, we've done quite a few events across the research professional and outreach space. We're also launching our first ever Pathways program to provide mentorship to students who are interested in pursuing a path in earthquake engineering, but just need some mentorship. So be on the lookout for that. But that's my pitch for the PSC. Reach out to me, Brian, or Saha for any questions related to that. But to kind of kick off the exciting stuff, I'll pass it over to Franco to get the show on the road.
Thank you, Omar. Hi, everyone. My name is Franco Mayorga, and I'm serving as an officer for the Peer Student Committee. Well, today we are joined by Jim Malley, COO and Senior Principal of the Corp Engineers. Well, Mr. Malley has over 39 years of experience in seismic design, evaluation, and rehabilitation of building structures. He has been involved and chaired numerous committees in AISC as well as SAC steel projects in response of the Northridge earthquake damage. He was also one of the authors of the Peer Tall Buildings Institute guidelines for performance-based seismic design of tall buildings. In 2021, he was elected to the National Academy of Engineering. Well, we are very excited to hear and learn from you, your presentation, Jim. The floor is all yours.
Okay.
Thank you.
Thank you very much, Frank. And it's a great pleasure to be here today with the peer group and share a project that our company did a number of years ago. But I think it's still very current today for kind of the state of the practice and maybe the art of seismic rehabilitation of existing steel moment frames. So I'll just jump right in. Okay, so I'm doing this. I'm going to get Franco back here. All right, so now I want to. Okay, can you see the presentation? I'll put it in mode once it's all there.
Not yet.
Not yet. Okay, sorry. One more. I got to do one more share. Okay, hold on. Sorry about this. Okay, so window. There. Okay, share. Okay. Can you see Brian's? Is that? Shoot. Try this one more time.
Yeah, I cannot see the presentation yet.
I don't know. It's not. Darn it! What did I do wrong? Sorry about this. I'm not a usual Zoom user. We're routine more. I'll try this one more time. Okay, so. Let me see. It says stop. It says your screen is sharing. It's weird. All right, hold on. I'll start over again. All right. Okay, window. Okay, I think I did window instead of entire screen. Okay, so now, okay. Okay, so now.
Yep.
Okay.
Now we can see the presentation.
Oh, perfect. Okay, great. Yeah, I hit the one wrong button twice. Okay. All right. So here's the title: Seismic upgrade of a 15-story moment frame satisfying performance criteria with application of experimental and analytical procedures. This was a project that Degenkolb did jointly with Crosby Group. Colin Blaney was a principal there at the time. And you'll also note that UC San Diego was involved because we had some connection testing that was involved with the project as well. So I want to recognize the contributions Crosby Group made to the project as well as the presentation. Okay, so we'll talk about a description of the building and the challenges and issues that we faced in figuring out what to do about the seismic retrofit. A little bit about the connection history. Franco mentioned the Northridge earthquake damage that sort of led to this project being tackled. The design criteria that we worked with, some schemes that we put together, and the one that we selected, how we did our analysis, an overview of the testing program that happened, a little bit about a connection design and a project summary, and I'll talk a little bit at the very end about some of the interesting challenges that we faced because we did the retrofit of this building. It's an office building in downtown Oakland while it was occupied. And so very interesting process that you have to go to make that happen. Okay, so the building is, as I said, 15 stories. There's a single basement level. It was designed to the 1988 Uniform Building Code. It was actually just in construction. It wasn't constructed. It wasn't constructed when the Loma Prieta earthquake hit here in the Bay Area. There were other buildings in downtown Oakland that actually did have some connection damage, like what happened in Northridge, that was found after the Northridge earthquake, but this building wasn't in that category. So you can kind of see there are the parking levels there at the base. Here down at the bottom few floors, and then offices above. There's an atrium here on one side of the building, an architectural feature, and this building is now a office building for the Caltrans, our state of California Department of Transportation. So there are hundreds of civil engineers, transportation engineers in this building that kind of control the work that gets done by Caltrans in the Northern California region. One of the other things that's very interesting is that this building hosts what they call the Traffic Management Center for the Bay Area, so that whenever there isn't any kind of an event, all the cameras that one would see about traffic in the Bay Area on television are controlled from this building. So this building is very important to Caltrans after a major earthquake. In dealing with sort of bridge issues or road issues and the like. So it's a pretty important building in their inventory. Okay, so structurally, it's a steel frame building, steel moment frame, and in the red you can see the moment frames that go around the perimeter of the building. And I mentioned that atrium here at the center on the top of the plan here. So that's the open space for the atrium. There's no moment frame that connects across the opening in the atrium, but there is a beam that runs across there. Mostly on the perimeter because the beams in the moment frames are quite deep. So having interior moment frames that deep would interfere with mechanical spaces and the like. So usually this is very common for this era of moment frames. There were a couple of moment frames here that sort of framed the sides of the atrium, came back into the building a little bit, and those were also moment frames. Okay, so what are the challenges? The poor existing connections that were identified by the Northridge earthquake, the bolted web welded flange that we call euphemistically the Pre-Northridge connection, that fractured in over 100 buildings in the Los Angeles region during the Northridge earthquake. This building also has some very deep columns and some box columns, as well as and very heavy W36 beams. So for those of you that are not in the United States, they're about 1 meter deep beams, and very heavy, very thick flanges up in some cases over 2 inches, 50 millimeters in thickness for beam flanges, much heavier actually than what anything that had been tested by some of the research that was done after the Northridge earthquake. We had a pretty strict drift criteria. I mentioned that atrium creates some like an irregularity in the structure. I also mentioned the occupied facility, the Transportation Management Center that's in the building as well. And every project, and we didn't have a lot of as-built drawings of the mechanical, electrical, and plumbing systems to work with in developing our retrofit design. So we had to do a lot of inspection in those systems to make sure that we were properly dealing with those in the design. And for every project, budget's an issue. Okay, so let's talk about previous testing. Because this building was occupied by folks from Caltrans, they were aware of the pre-Northridge problem and the damage that had been done to steel moment frames. And they also knew that they were in a building with large steel moment frames, larger than any that had been tested. And so they were able to get some money from the state of California to do some testing that simulated the connections in their building, which is very unique. I've never had another building where someone, before we started the work, said, here are some tests on the connections in our building. And you can see here one of the tests with a W27 by 281 column and a 36 by 210 beam, quite large, done at UC Berkeley by Bozer Stojanovic and Steve Mahan. And similar to what we had seen in other pre-Northridge tests, fracturing of the connections that you can see in the blue circles at the top and bottom. And then when continuing the tests after the fracture, what happens after the fracture is that the couple between the top and bottom flange is lost. And then the couple becomes the flange in compression plus the bolts in the web, so creating a much less capacity. And you can see that big drop off here to where now the bolts are working with the two blue circles to the left and right of the slide. And then the little drop offs that occur down to the end are when bolts are fracturing to get down to very limited capacity. And you can see the drifts here. So the drifts failing around 1% on the bottom flange fracture, and actually less than 1% on the top flange fracture, which was the first time we had seen this before, where the flange didn't even reach sort of the yield strength of the beam before it fractured. And so this was concerning to us, at only reaching about half of MP of the beam. Most of the other tests, previous tests, had all been able to reach sort of the MP before fracturing, and getting out to about 3% or so before basically having very little moment capacity, still some shear capacity with the remaining bolts. Okay, so as far as the design criteria goes, from the state of California, and Caltrans and the owner of the building, which is the Department of General Services, they wanted minor structural damage that was repairable. They wanted moderate non-structural damage, which could have a lot of repair. The disruption of the systems for days to months, returning to occupancy within weeks with minor disruptions. Now that was the formal definition that they wanted for the building, but actually the building occupants were worried about this not being a high enough level because of how important the traffic management center was to them. So they said, gee, if you really could do a little better than this and move us up one level, that would really be helpful. So we ended up using we had a peer review panel, or a peer review board here, PRB, and they established a drift limit for us of 1.5% drift at the design basis earthquake. And again, these buildings will start to yield, if they go beyond without fracture, at about 1%. So about 0.5% of nonlinear behavior to reach the design basis earthquake, the earthquake that comes about once every 475 years. Okay, so here's some information about that previous testing, the layout of the lab at Berkeley on the strong floor, simulating the column on the left and the beam coming across the slide, and then some fracture pictures here. You can see the size. These are quite large, and do make a lot of noise when things break. So we do have some videos here. Here's that image of the test here in the lower right, and then you can see in the lower left here, the flange closest to us has already fractured, but the other one has not fractured. So this is in tension on the flange closest to us, we have that couple between the bolts and the other flange. Then you'll see that on the upper left, you'll see the fracture coming right in front of us, and then some breaking bolts on the upper right here. So let me get those videos started, and you can listen for the fractures, breaking bolts, etc. You can see that fracture on the upper right there. And then now the bottom flange here is in compression. The flange is broken, so we're breaking the bolts as we go through, and that's when you can see the reduction in the capacity. So quite a dramatic test to preview for fun. Okay, so based on that, we developed four different strengthening procedures or schemes. One was basically we call connection modification, and if you will, that was just fix all the connections. I called it the brute force approach. So we're going to go in and modify all the connections to avoid the pre-Northridge performance. The second approach was doing some of the connections, not all, but also adding viscous dampers to reduce the demands on the connections and the drifts in the building. The third approach was another sort of brute force approach, basically changing the lateral system. In this case, we talked about, going to more of a dual system where we would have the existing building moment frames, but then also adding a full brace frame on those moment frame bays around the perimeter. And then the fourth was doing a base, shouldn't say base isolation, because this was looking at isolating at the top of the parking garage just below the office space. And the reason for doing that was that this building was going to be occupied during the retrofit, and having an occupied building, if we could limit, or if we didn't have to do any work above the isolation plane to keep the demands on the existing connections low enough, then we wouldn't have to disrupt the occupants. And there's a lot of costs and disruption that goes on by having to do that. So we looked at that scheme. We looked at a bunch of different parameters here. You can see the duration of the work, the duration of phases, the number of enclosures we'd have to be in, how many parking spaces we would displace. We tried to think of everything we could to try and help with the decision process, because we wanted to bring the owner into this process. It wasn't just us as the engineers deciding what to do. And that really, so we had to get into a lot of different things. Another part of it was what we thought the structural performance would be. And you could see we thought base isolation would be probably the best. And maybe the dampers in a lateral system and buckling or strain brace frames would be second. And then maybe the connections would be adequate. Construction costs obviously is important. Base isolation, most important, most expensive. How long you're on site, disruption to the occupants, post-earthquake impact and appearance of the building, post-earthquake retrofit impact, or on the occupants, the repair costs, impact to utilities during disruption, and post-earthquake disruption time. So we tried to throw everything we could at it. In the end, we ended up going with scheme number 2, which is the connection modification with dampers. And we'll talk about that scheme. So, so that was the scheme. So we installed the dampers in the same locations as we're doing the connection strengthening. So we've got a moment frame there. We can put dampers in place in line with the existing moment frames to kind of minimize how many places we're working in the building. We tried to use as large of dampers as we practically could to minimize the number of locations, because every time you touch a space, it costs a lot of money. Worked at the perimeter where those were, and that actually helped us to minimize the disruption to the mechanical, electrical, and plumbing systems that feed the rest of the building. We did have to do some column splice strengthening along the moment frame columns in a number of places, and a few collector beam strengthening to make sure we could deliver forces mostly across that opening of the entryway over the entryway of the building. Okay, statistics on the scheme. There are 1,218 existing moment frame connections in the building, and we're touching about 60% of those. We touched about 60% of those. We ended up with a double haunch type of connection, and I'll tell you that I'll go and get into that a little later on as to why it was a double haunch. We had 60 connections that have both a haunch and a gusset plate for the dampers, and 76 of the connections have double gussets, so a gusset on the top and bottom. I'll see some of those. I'll show you some of the different images for that. About 228 dampers total in the building, mostly around 450 kips. 650 kip dampers for some 50, and then 24 smaller ones up toward the top of the building. So here's what the scheme looked like. And so what we did here, you can see the dampers have been added, and then also where the connections are modified, where we've kind of shown these little extra work shown there. One of the reasons for sort of spreading it around was we wanted to minimize the amount of column strengthening that we would have to do, because if we just stack them straight up, we would have had to have done some massive strengthening on the columns toward the bottom of the building. But this way we sort of spread the overturning out to as many of the columns as possible. This also reduced the demand on our foundations. And this has a matte foundation under it, so there's no deep piles or anything. And, we don't really have any uplift control. So we had to really try and not put too much local demand on the mat, because doing foundation retrofit as part of a seismic retrofit becomes very expensive, especially when you're, one level below grade. So that's one direction. Here's the other direction. So this is the architect that we worked with. One other thing is we were actually the prime consultant on this project. So the architect and all the other engineers worked for us. So we got to sort of drive the train rather than the architect, which is more common on new construction. The architect sort of dubbed this elevation the spaceship, sort of because it kind of goes up like a spaceship, I guess. But again, same concept of spreading the dampers out to touch all the columns at some point, so we could minimize any kind of strengthening the columns. All we actually had to do was to do some column splice strengthening. And then on the right there is an internal elevation for the moment frames. And we didn't put any dampers on those because, again, there's a lot of traffic, internal traffic in the building. That would have really disrupted the operations of the building. So we just strengthened those internal frames on either side of the atrium. Okay, so these are what the connections look like in various configurations. You can see the sort of our little BIM models of the different haunch connections, or the internal center connections where we had two-story X's for the dampers, and the gusset plates that had to be added for the construction. And obviously the dampers came in with pins to allow easier erection, working in a space, an occupied space, didn't have a lot of room to move around. We'll talk about that a little bit as well. Sorry, let me get a little bit of water. So here's what the rendering of the retrofit looked like when we presented it to the Caltrans, the owner, to make sure that they felt that was okay. We also had to kind of get this cleared by the city of Oakland, that they didn't feel it was too impactful on the street venues, etc. They ended up trying to match the granite that was originally done. That was their original plan, but they actually ended up getting away from that, and they went to more of a steel, anodized steel, kind of a dark, trying more to just match this dark gray color, because they couldn't find granite to match what was there. So they just said, okay, let's not match it. We'll change the color. So that's that. Here's what they look like sort of inside the office space, and they're quite large, obviously. They can get up to like 18 inches in diameter. So they do impact some of the windows. One of the things I didn't mention, let me go back a little bit, because this is, I like this story a little bit. When we look at the elevations, notice that there's also a short bay. Most of the bays are about 30 feet long, about, a little over 9 meters. And then there's a half length bay, 15 feet. And all of the supervisors or the leaders of the office had their offices in these corner spaces. So we thought it was pretty smart to not put dampers through their offices. So we avoided all the major offices with the dampers, just to stay out of trouble with the people who are making decisions. Okay, so let's talk about the analysis, talk about about the ground motions, about the models and some of the results. As I mentioned, we did some preliminary studies using a couple of guideline documents, the FEMA 351 guideline, as well as two different approaches. This was a document that was published after the SAC project for seismic evaluation and retrofit of existing buildings. So we had a couple of different results there, and then in discussions with our peer review board, they said, let's just go for 1.5%, and that's kind of what we designed to. Okay, so here's the spectra that we worked with at the time. We had sort of peaked out the spectrum at around 2.4 G in the short period. The building period is out here at about 2.5 seconds. And so the base shear is around 0.6 G that we had to design for. You can see the some of the ground motions that we went through. At this time, we were just doing 7 ground motions. If it was done today, we would probably do 2 sets of 11 using 2 different periods. But at that time, we weren't doing conditional mean spectra. So we were working with about 1.4 of the design basis earthquake as the average for the spectrum we wanted to work with. So you can see that there. So we did do nonlinear time history. One of the things that was really sort of forward-looking in our model was that we modeled the fracturing of the existing connections in the building, because again, we were only touching 60% of the connections, so 40% we were leaving existing connections in the building. So we needed to make sure that if they did fracture, they didn't get so far out to the end that we didn't have gravity. We could still resist gravity, which we felt like, if we stayed below about 3% drift. So in blue here is the test result, and in red is our simulation of that with the fiber model. So basically what we did was we took a fiber that had the area and volume, or the capacity, yield strength and tensile strength of the beam flange, and then a similar fiber at each bolt location, and then rigid elements in between. And the bolt locations basically went up to yield and then broke. The fiber would break. And we basically just took the AISC specified FU for the bolts and the area of the bolts, and just went up and put the fiber to fracture at that point, and that's what came out in the red drop off. So this is when each bolt breaks and we lose capacity, and we were pretty happy with how that matched the tests, and we did all 3 tests that we had to work with, and implemented that on all the existing connections. That made for quite an extensive model, and took a long time to run back in the day that we were doing this. So on the modeling side, we did nonlinear modeling of our dampers, obviously, with the coefficients and things that we talked about, the C coefficients and the like. The column hinges were basically elastic, and then so like a yield plateau at some point. Then we had beam hinges. Back up a little. So beam hinges, and this would be for the retrofitted connections, and then panel zones for the beam column joints using, and we were doing this in Perform, the nonlinear analysis program. And then OpenSeas wasn't around in those days. So, and then finally, soil springs. So we did put springs under the mat to simulate the soil. So having no capacity and for tension, and then kind of a linear piece, and then a secondary stiffness, and then yielding of the soil to make sure we weren't going to have any soil issues. So a lot of nonlinear elements in the model. Okay, so the first thing we did was we built that model for the existing building without any retrofit, just to confirm in our minds that, hey, this building really is would not behave well in a design basis earthquake. So here's the results of that. You can see the ground motions that we did. So I guess we had about 13 ground motions there. I forgot about that, or 14, I guess. So 14 ground motions. The average or the mean of those is here in black with the dots, and this is sort of a strange picture because the floors are here on the bottom axis, and the roof of the building is over here on the far right, and the ground floor is over here on the far left. So you have to kind of turn your head if you want to think about drift over the height of the building. But what we were finding was that the drifts were really focused in the worst, primarily, and for most all the ground motions in the parking levels, here between level 2 and level 5 or 6. And we were getting up to 4.5% drift. And if you recall, the peer review board said 1.5% drift is the target. So we weren't even close with the existing building. And some of them were up at 7%, where, you know, you can be the judge if the building's going to collapse at that point. So we didn't want that. So we moved on then to the next one we did was you said, okay, now let's do a model, even though we weren't going to go after this approach. And this was part of the reason that we didn't use this approach. We modified every connection in the building, no dampers, just connection modification. So the brute force approach. And you can see that definitely helps, but we're running around, instead of 1.5%, we're running around a mean of about 1.8%, and some of them getting up close to that level where we feel like we may be losing gravity on some of these connections at around 3%. So didn't feel real comfortable about that. Obviously, the damper scheme is going to do much better. A lot of scatter in this because of the fracturing of the connections. Okay, so here's the scheme that we ended up with 60% connections and dampers. And again, we kind of played with the number of connections and the size of the dampers, et cetera, to get this kind of result. Very close to about 1.4%. So we had a little bit of margin below 1.5. 1 or 2, motions which is common in this kind of analyses, that sort of took off a little bit. But even at that point, we were only about 2.2% drift on this one motion out of 14, that we still felt comfortable about the gravity performance, even if we did break a connection or two in some of those levels. Okay, so and let's see what's, so this one we did not design basis, but maximum considered earthquake. Now we didn't have to do this for the criteria, but we still wanted to feel like if the magnitude 7 point something happened to hit Oakland on the Hayward Fault, and we did get an MCE event, how would this building do? We didn't have to present this to anyone. I think we did anyway, because we thought the results were pretty good. So the drifts now go up to about 1.8% in general. And the very worst we got at 1 story for 1 ground motion was right up at that 3% level. So, you know, potentially maybe some beams at that level might lose their, be down to 1 or 2 bolts hanging on in some of those connections. But we felt like that was pretty darn good for the MCE level of response. Okay, so here's a video that's going to start up here. On the left is the damped building, the retrofitted building. On the right is the existing building going through the same ground motion. And you'll start to see some red popping up here where fractures are occurring in the beam connections. And basically, when you see a half a beam, that means the left side is fractured, the right side hasn't. Once the other side goes, both sides, they'll turn red here. You get, yep. So it didn't do very well there on the right, especially down in the lower levels where every connection is broken. You can see on the left, we do have a couple of fractures just above maybe where we stopped some of the bracing in those shorter bays. One of the reasons that we ended up, one thing we did at the very outside of the building, and you may not have seen that in the slide of the elevation, was for those short bays, the 15-foot bays on the corners where the executives had their offices. Those bays are moment connected, or were moment connected, and we actually removed the moment connection on the end of the beam at the corner of the column, at the corner column. One reason is because we'd have biaxial bending in that beam and that column that we didn't think was great, and also to reduce the demand on the moment connection, because the shorter span is going to go through twice as much rotation to get to the same drift level as the longer span beam. So that was part of a retrofit. So in some cases, it's not, you don't strengthen, you actually weaken in order to get better performance. So that was a little bit of an interesting observation that we made. So energy dissipation plots we took out, and this is kind of interesting in that a lot of what's going on here and down here in the red is what they call dissipated inelastic energy. So that's damage to the steel frame. We've got some modal damping damage for a lot of the rest of it. If we then fixed all the connections, you can see we still have a lot of inelastic energy in the frames, a lot of damage to the connections. If the building was still salvageable, we'd have a lot of connection repairs to do after that if all we did was fix the connections. So the third one is the final scheme. So now we've got this big white band, which is all the energy now gets, or 60 or 70% of the energy is now in the viscous dampers, and not nearly as much down here at the bottom in the damage to the frame members, the steel members. And the dampers can go through multiple earthquakes without any trouble at all. And so that, you know, kind of validates the idea of how much viscous dampers can help these connections or these systems. One of the other things was that we found was that the damping also really reduced the accelerations that the building would potentially see. And the California Building Code at the time had a force equation that would require us to anchor equipment or design diaphragms for the yellow line here, which actually goes up to 2.1 G for if you start out at 0.6 G, like we had to do for this spectrum, very high, obviously. When we ran the nonlinear analysis, if we had just strengthened all the connections, we were getting up in the 0.9 G area here, maybe over 1 in some cases. But when for the damp system, the accelerations were right around that 0.6 G number, which is actually much more manageable. probably much less damage to the architectural elements that are sensitive to acceleration. Now, I will say that if we did base isolation, that would probably have been down in the maybe 0.3 G. And that's one of the big benefits of base isolation, is reducing the accelerations in the building above. But it was a lot more expensive and more disruptive and all kinds of other things. So, okay, so that's the analysis. Let's jump to why we did project-specific testing. And so I think we talked about this a little at the start. The sizes of members and the type of members in this building are quite different than what had ever been tested before on retrofitted connections. And we also felt like, you know, we did have some good details for smaller beams and smaller columns that had been retrofitted, that had been tested. But given how poorly the big, deep sections and heavy sections on those existing connections that I showed the videos of had done on the Berkeley test, compared to what we saw on all the previous pre-Northridge tests that were able to get to yield and do a little bit of yielding before fracture, whereas some of that 3 of those tests all fractured one flange at only about 50 to 60% of the capacity of the flange and never even got to yield. We felt like, I don't really want to extrapolate the retrofitted connections beyond what had been tested before. And so we came up with a program to do the tests. Oops, what happened here? Okay. And we did double-sided tests because we wanted to pick up that effect rather than single-sided tests that are a lot of the tests that were done previously. We wanted to include the slab, because the slab does affect the response of the connections. We found that in some earlier testing. Anything that was originally the part of the pre-Northridge connection, we used with the older weld metal that we don't use anymore. That was used on those welds, but then anything that was part of the retrofitted elements, we used the latest welding material and welding procedures to try and simulate what would happen in the building as well as much as we could with the tests. So one of the other things that we tried to simulate was how the building would have originally been welded. And on the left there, you can see that one of the test connections being welded up for the pre-Northridge welds. And this is what's called, they used to call the wildcat position, because the welder sits on the beam flange and then now he's welding the top flange. But imagine if he in this case had to reach down to the bottom flange down here, which is 36 inches away, leaning over the side of the beam, and then welding through the access hole, is one of the reasons we found that the welds were not done very well. Theoretically, there should have been in a chair on one side of the beam to make the weld, but that's, they had to have chair on either side for them to get down and do it. So this was the way that those welds were made at the time that this building would have been constructed. So tried to simulate the kind of poor welding we would expect at the bottom flange. For the retrofit welding, because remember, all these frames are on the perimeter of the building, we tried to simulate, because one of the kind of the no-goes on this whole project would have been if we needed to take the curtain wall off the building to do the retrofit, because we would never get it back and waterproof, and there's all kinds of problems with that. So we had to verify that whatever we designed could be done with the curtain wall still in place. So what we did, you can see here, is we built a plywood wall the same distance, and we measured this and checked it against the drawings and measured it in the field. The distance from the plywood wall to the steel frame was the same as it is in the building. And then we made the welder do the welds that they were going to have to make with our retrofit design in that same way. So you can see here that at first I thought, well, gee, there's so little access. We're going to have to get very tall, thin welders with really long arms in order to make these welds. But you can see that wasn't the case for this welder that did the retrofit welding. And in the end, they they were able to do it. They said it was difficult. They had to do some extra planning, and it took longer, but they were able to do it. And we use these pictures actually to verify for the bidders on the project that it could be done, because the first question they all said is, how are we ever going to do all these welds when it's so close to the curtain wall? So we did that, verified it, and in the end, they were able to do it as well. Okay, so this is what the test setup looked like at UC San Diego. You can see the actuators at the top of the screen, and then the slab on top of the beam. This is simulating a damped frame, a damper on the right side coming in, and then just a haunch connection on the left side in this test. I forget that this is test number 4 of the sequence. But that's what the test setup looked like. So we push back and forth on the actuator with a pin at the base to generate the moments and shears in the beam like they would be in the test. So to simulate the slab, we put the metal deck, the rebar, just like was in the details on the existing construction, and then place that before the test. So here are the 4 tests that were done. And I just want to mention the testing program and the analysis that we did cost about $250,000 at the time. But if you recall, the retrofit was about $40 million. So in my mind, it was money well spent to learn, and you'll find out why here in a second. So the first test we did was trying to simulate the, trying to work just from below. We wanted to be able to not have to touch the top of the top flange, because we would have to remove the concrete slab and replace it. And then we would be disturbing 2 floors at once. Again, remember that this is an occupied building. All the work is being done at night, but we wanted to at least have the workers in the office space be able to work until the actual work was being done on their floor or above their floor. So that was the first try. That you'll see that didn't work. So we actually went to a double haunch and sort of bit the bullet that we were going to have to pay the extra and have the extra disruption. Then we looked at a test with all bolted connection, number 3, where we would be able to avoid welding. And this was attractive and had worked on smaller sizes in the past. And it was attractive because not having to do welding in the field, we didn't have to do like a fire watch. We didn't have to have smoke evacuation, because we would get complaints from the workers the next day if they smelled smoke in their spaces and things like that. So it saves money. It's less trouble. So if we could do the bolted one, we figured we'd give it a try. And this is called the Kaiser bolted bracket. These are cast brackets, and they're quite large. We actually have one from the test and one in our San Francisco office as a memento. And then the 4th test, we wanted to simulate the condition where we had dampers coming into a bay, right? So on one side, no damper, the other side dampers. And because this is a different configuration, we wanted to make sure it wasn't going to change the response of the connection. One other thing we looked at in finite element analysis was how much the damper forces themselves, the axial forces from the dampers, would impact the demand on the connections in the finite element models. And we found that it was actually pretty minor, which is why we didn't put any kind of force from the braces on the test. It really was driven by the moment frame action, not so much any extra forces induced by the dampers. Okay, so I kind of talked about this, so I'll go through this quickly. They had done there had been bottom weld haunch tests done previously on smaller sizes. That's documented in an AISC design guide. This one allowed us to work from the underside. I still wasn't convinced on the larger shapes that we were working with, so I wanted to add two what I called fin plates welded up to the bottom of the top flange and the face of the column to kind of strengthen that and reduce some of the demand on this weld, because once you strengthen the bottom flange, it adds demand to the top flange weld. Usually almost all the fractures were on bottom flanges for the reasons I talked about, the welding reasons and challenges I talked about a little earlier. But this would now create some more demand there. So I thought, okay, let's try and strengthen that from just being a single flange to being the flange plus two, kind of a double T, if you will. And you'll see that it didn't quite work out. So this is what it looked like in the field. You can see kind of the scope and thickness of the plates, and the haunches were quite large. We tried to do some calculations where we could limit the stress in the top flange weld to something below we thought was going to be fairly low, and keep it away from fracturing. Didn't quite work out that way. Because after a couple of cycles into, I think, the 2% drift cycles, so we went beyond yield. We could see yielding in the steel from flaking of the paint, whitewash paint. We actually fractured at the top flange all the way through the flange, across the web, all the way to the other flange, and it sounded like, you know, like a bomb went off in the lab. My client was there, and the client was a civil engineer himself, who was a project manager for the state. And he looked at me and said, "I hope we can make the next test work." And I said, "Yeah, we'll figure it out." So we went to that double haunch, and I told him, I said, if this doesn't work, we were in San Diego. I figured I would just drive my rental car across the border to Mexico and never be seen again. Because I wasn't sure what we would do if we couldn't make a double haunch work. So here's the double haunch. So you can imagine a haunch on above the top flange as well. And luckily that did work. We got out to 5% drift. You can see some yielding in the flange, and not much buckling because of the thickness. The width thickness ratios are very low on these beam elements because it's such a stocky shape. And we're able to get to 5% drift. We were trying to get through the 4% drift range without any kind of fractures or things. And we were able to accomplish that here. Eventually, at the end of the second cycle and the 5% drift, we did get a fracture adjacent to where the haunch came into the beam flange. And this is sort of, I guess you'd call it low cycle fatigue, because there's so much demand back and forth, shear strain being sucked up in every one of those cycles, that eventually something has to break, kind of like a paper clip, right? If you keep twisting it enough times, it's going to break. So you can see still had some panel zone yielding in here, even though it was double haunch, and we did some finite element models on that later. But we did very much protect the existing brittle welds from fracture in this detail. Did a little finite element analysis, the test and the results, pretty close agreement, felt good about that. So the fourth specimen is the double haunch with the gusset plate for the damper. And that's what that looked like at the end of the plate. That had thinner flanges, so we saw more buckling, but again, got out to 5% drift. And this is what a test looks like at 5% drift, so it's pretty dramatic. And you can see there, when the compression flange doesn't fully straighten out, it's because it sort of tips a little bit as well, and got good performance there. So it's very similar to test 2 as to when we got the fracture in the welds. And again, we felt pretty solid about that because we had multiple cycles at 1% drift, 2% drift, 3% drift, 4% drift, and 5%. Very large demands, probably more than we would ever actually see in one of the connections in a ground motion. Again, model with the finite element looked good. And then these are all the tests on top of each other, sort of showing the differences between the 4 tests. I didn't show you too much about the third test, but we'll show you that in a video here in a second. We did some finite element analysis to compare the test 1, 2, and 4. And you can see the interesting thing about the single haunch is that on the Pre-Northridge, you can see very kind of high shear strains in the column panel zone. And that's what leads to what we call kinking. And you can see that a little bit here in the flanges here, where you don't have a straight line here. It sort of has a kink at the corner of the panel zone here. very high strains happen there. And that's what causes, when you have weak panel zones, you are going to get a kinking in the flange. And we've seen that fracture in the Pre-Northridge connections before we get much yielding out in the beam. And that was the configuration that was in that situation in the existing building. When we put the bottom haunch on the right here, that didn't really take away that yielding in the flange and in the panel zone. So we still had that kinking going on, and this is where that fracture occurred in that top flange. So pretty interesting result. Once we went to the double haunch, you can see the panel zone gets very quiet, not much yielding going on. You're getting a little yielding in the web of the member, but that didn't really, wasn't anywhere near any of the welds that would fracture. And so, kind of validated that the double haunch was a really good approach. This is another kind of way of looking at that on the original design. You can do, this was from I think from the finite element analysis, you're getting a rotation of about 1 and still getting about 0.8 at the same force level with test 1 with the single haunch, but that drops down even to 0.6 in the double haunch. And you can see the reduction in shear demand that goes on as well in the panel zone. So it really helps to quiet down the panel zone and that kinking action. Okay, let's talk got a couple minutes left. Oh yeah, a couple minutes on the occupied facility issue. Really is challenging because you're working, you have to deal with noise and dust control. We actually put monitors because there were residential buildings within a block of the building, and we were going to be working at night with grinders and things that make noise. And don't forget, some of them are in a parking garage that's open. So we had to monitor the noise so that we wouldn't get complaints from the neighbors. For that, dust control, obviously within the building, disrupting the operation. So you really have to understand how the facility works in order to design the construction, if you will, and put the requirements on the contractor as to how they can build the retrofit with minimizing the disruption as much as possible. So you need to spend a lot of time with the facilities people, understand what the enclosures are going to look like, maybe do some mock-ups and show them that, making sure you've got power because the welding obviously draws a lot of power. What do you do with the smoke? I mentioned that previously. And then could we ventilate to the exterior? So could we break out or take out a window to ventilate, or do we have to go all the way up to the roof through the mechanical shaft to ventilate the smoke? So all those things that you have to think about, not just the structural part when you're doing these kind of retrofits. So you have to look at all the systems, think about, that this is a 24/7 building for that transportation management center. So we needed to be very tight about the work that was going on and making sure that we weren't going to cause any outages to that operation. One of the things that we did was we made phasing plans. And basically what happened, what we did was that we gave the contractor 3 halves of a floor. So the first half of the floor would be where you're doing the demolition to clear everything out to do the structural work, which is the second half. And then the third phase is the replacing all the non-structural to get it back for occupancy. So we sort of kind of looped up the building, taking 2 halves on one floor and 1 half on the floor above or below, and then kind of spiraling up the building to do the retrofit. So again, kind of work that out with the building owner and then communicate it with the contractor. So when you're working in a building, you need to know what's important to the owner, work with the facility staff to develop performance-based requirements that kind of handcuffs the contractor to make sure the building is working properly during the construction, and then make sure they're doing what they're supposed to do. We really get in trouble if the contractor doesn't follow the rules. So final thoughts, combining, connection strengthening and dampers met and really exceeded the client's goals for the performance. The nonlinear analyses that we did were a powerful tool to evaluate and design the connection retrofit, and led to a more efficient design. It was less less costly than it would, much less costly than it would have been if we'd done an elastic analysis. The dampers also reduced the floor accelerations, and we really did need to do that project-specific testing to make sure we got the right answer. And then working in the existing building requires extensive planning, coordination, and work with the contractor. So let me get out of this real quick. And if you've still got a couple more minutes, let's see here. I've got a 2-minute video. Let me see if I can get that going. Okay, can someone tell me if they can see that?
Yep, yeah, we can see it.
Okay, great. Okay, so this was some video that was done by Professor Wong at UC San Diego that did the testing for us. I call this the 10 o'clock news video because they basically just show the last few seconds before something breaks. But you know, obviously these tests take many hours, and you can see steel bending back and forth. But they did just do you know, the very last part of the test. So you can see how long ago these tests were done. And this was I mentioned all the cycles that we put the connection through. Here's the first specimen with the bottom haunch. That you can see the size of the members, welded bottom haunch with the vertical ribs. The test setup, we've gone through that. And okay, so about the first negative excursion to 2% drift. Watch up at the upper where the arrow is and listen for the bang. Yeah, I thought everything was going really well until that point. It didn't look like anything was happening, and I was actually on the phone with another client and had to say I have to get off the phone, but it wasn't a good day. Here's the second test with the double haunch. Again, test setup. So now we're out at that 5% drift where I've said, you know, we've got to beat this thing up pretty badly. And you can see some yielding and the like. It still looks pretty good, right? But then, so again, quite a loud noise. But way out there. So obviously much better performance. Third test. Now here's the bolted one, which I didn't talk too much about. So we've got these Kaiser bolted brackets, deep beam and column. The casting of the brackets, we had to use 1 5/8 inch really big bolts to get enough capacity for the brackets to work. We did get it out to about 4% drift, and everything looked pretty good. But then the bolts started flying all over the lab. So watch to the bottom left there. So the head of that bolt ended up about 70 feet from the test specimen. So here's farther along, we'll just keep breaking bolts. So not real good there, but we're at 4%, you know, it was kind of close, but we said, yeah, I don't think so. So that was kind of quiet after seeing all the other stuff. I think, is there one more? I think there's one more. Yeah, here's the final, the denouement, if you will. I think that's it. Okay, so yeah, the bolts started fracturing here, so it didn't really meet our 4% that we were targeting. And then, oh yeah, that's right, we didn't have the video of the fourth test, which was very much like the second test. So I'll get out of that and I'll stop sharing, and I think that's it. So can you see me now?
Yep.
Great.
Thank you.
Sorry, I went a little over, but you know, interesting project. One last thing about the brackets. The bracket manufacturer came to the test because he was very excited he might get this big retrofit test. And when the bolts started flying all over the lab, even though his brackets looked perfect, you could see him hit all the blood went out of his. He got very pale because he was so he knew that he kind of thought the project wasn't going to go his way after all those bolts were running around, were flying around the bolt on the lab, unfortunately. But I think it does work pretty well for smaller conditions where you can make the the bolts can have a higher factor of safety than they had in this test. So anyway, sorry to go over a little bit, but hope that was enjoyable.
No, I think we're good. So yeah, thank you very much, Jim, for the great presentation. It's always good to hear from you and these special projects. So yeah, I think we have just a few minutes so we can go over some of the questions from our audience.
Okay.
And yeah, so let me get started with the questions on the chat, but then if anyone has additional questions, feel free to just send a message.
Yeah, please.
So which degradation hysteresis models were used for the connections and also for the soil springs?
So on the connections, we didn't really use a degradation model because we were using the fibers. But the beams themselves outside the fibers, you know, it's been a while. So I don't really remember the answer to that. And so sorry about that. But yeah, I don't remember exactly what we did on the degradation models, but we did. I don't think we had degradation on the soil because as soon as we got uplift, we would have called it off. So I don't think the compression side would have ever degraded the soil. We probably just kind of yielded before it ever degraded. But on the beams, we did do degradation outside as well.
Nice. Okay. If I am correct, this were the nonlinear response history analysis done in Perform from the screenshots? Yeah. Nice. So, well, other question was, could you comment on the decision of not having out of plane restraints in the middle of the fluid viscous damper connection in the work point of the dampers?
Yeah, that's a good point. Let me think if we did. I don't know that we. I think we might have, to tell you the truth, but I didn't show it. But I do think, I'm pretty sure we did, because I'm almost. In some cases, there might have been one already there. But also in one direction, we would have put them there. In the other because the beams were running parallel, so there wouldn't have been a brace at that beam in that case. But in the other direction, there's beam framing in pretty close in both directions for gravity, and we check the stability that gets created by the condition in that case. So we didn't have to put one also like they were 5 feet away on each side. So the beam flange was stable to get to the bracing, the existing bracing. But in the other direction, we did brace it. So that's a good point I didn't mention.
Gustavo also asked if you did any checks for residual displacements after the retrofit.
Residual, yeah. We would have at the time. I don't recall it being too bad because again, for the DBE, we were only at 1.5% drift for most of the cases. So you wouldn't expect much residual drift in that case. Very, very small residual drift is what I would expect. But and at the MCE, there potentially could have been a little bit of residual drift in maybe one or two of the ground motions that pushed it pretty far. But that wasn't a thing back at that time. Yeah, that certainly would have been something we might have been in our criteria now, just not a single drift level, but a residual drift check as well.
Jorge also sent us a message. How long did the project take to complete, especially in the consulting phase?
Okay.
And including the testing.
Sure. So we started this project at the gosh, it's almost 20 years ago. At the end of 2003 is when we had the first meeting, and we did those tests in 2005. And it took 3 years to do the construction from the start to the finish. And so that the design work was about 18 months from the very start to turning in the drawings, and then they had to go through the bidding process and the like. So yeah, it took about 18 months for design and then another 3 years for the construction. And again, that was primarily because they had to like hopscotch around the building and do all the phasing for the occupied spaces. So it took a lot longer because of that.
Yeah, I see. Sayan says, if you have checked the performance level of that building after a specific event.
So yes, so we've checked it both at a design basis earthquake with 14 different ground motions to meet that spectra, and as well as we did some checks also at MCE for 14 more ground motions at the higher demand. But I don't know, I don't remember any specific ground motions, if you will, if that's what the question was.
Yeah, Ritish asked, did you compare with any other damper configurations for better results in the software than the one you showed in the presentation?
I'm sure we did. But I know a lot of what we did was we were trying to, and we didn't want to get, well, we could have looked at single story dampers, all the way across the bay. They're flatter, so they might be a little more efficient. But again, we were trying to, we really were focused on schemes that we could really control the forces on the columns, because if we started having to mess around with the columns more than just fixing column splices, the cost of the project was going to get really out of control, and also how to retrofit the columns when they're so close to the outside of the building. So that really drove a lot of what we did. So I think generally we did look at the 2-story X kind of configuration for the most part. Yeah.
Nice. Yeah, I think with that, we have come to the end of today's seminar. Once again, I want to thank you, Jim, on behalf of the committee, and thanks everyone who attended the seminar. So stay in touch with the Peer Student Committee, and have a good day.
Yeah, thanks very much. Appreciate it. It was fun.
Thank you.
Thank you.
Good luck, everybody.